All right, so today we're going to be looking at complex numbers, section 0.4. You can open your textbook to page 51 as I call out some problems, and that's where we're going to be for homework. Complex numbers. And again, I'll show you my lecture notes as we go through the end of the day here. So what I want you to do is I want you to consider this problem. So I want to solve this. In the process of trying to solve this, we would subtract, we try to factor it, we try to do that. We can do the quadratic formula because we've learned that now. But if I just try and solve it by moving that over, I'll get x squared equals a negative 1. So the question is, this thing it's saying here is, there has to be a number that if I square it, I get negative 1. Is that even possible? And the answer to that would be not in the real numbers. There is no real number that I can square and get a negative value. The real numbers are on the number line. Any positive number that I square will give me a positive answer. Any negative number I square will give me a positive answer. If I square 0, I get 0. So there is no real number on the real number line that will square and give me a... Well, that doesn't deter mathematicians. They keep on going. They see patterns. They work with the patterns. And they came up when they started coming across this way back in the early, 1700s, I think it was 1600s. They realized there has to be more out there than what we're familiar with. Okay, and so that's where this numbering system comes from. Okay, so I'm going to give you the real quick nesting of our number systems. Okay, these are number groups that you are familiar with, and then I will talk about this new one, which is going to be called the complex numbers. And we're going to define that and work with it and see everything about it. So here's how it all works from your life experience so far. I'm going to skip the counting numbers and go right to the whole numbers. Whole numbers are literally the place you started in grade school. The whole numbers, these are 0, 1, 2, ... So basically you're counting numbers plus 0. These are the whole numbers. You started there. The next thing you did after that is you started branching out. You did some decimal numbers. You did some fractions and stuff like that. Eventually, you got to this thing called the integers, and they brought in this thing. So that's the next size group is actually integers. Even though it took a while to get to it, the integers, I forgot my key there, integers, are all the whole numbers, and then the negative versions of those. So negative 1, negative 2, negative 3, and so forth. Okay. So the integers are negative 1, negative 2, negative 3, 0, 1, 2, 3, and on to infinity in both directions. So if I have a whole number, I have an integer. If I have an integer, okay, it doesn't necessarily mean it's a whole number. After that, this is where all the decimals and the fractions come in, or some of the decimals and fractions come in. And it gets to the next group that you dealt with. And I'll just put it like so, because we have a lot more of these things. And you get what's called the rational numbers. What are rational numbers? There's a couple of ways you can define rational numbers. One is this way. Any number that can be written in the form P over Q, where P and Q are integers. So that's one way. Can I write it as a fraction? Okay. Another one that can be harder to see sometimes, or is this one. The alternate one is any terminating or repeating decimal. So if I have a number and I write it in decimal form, if that decimal stops at any time, it's called a rational number. If that decimal is a repeating decimal, no matter how many digits repeat, if it's a repeating decimal, it is also a rational number. That means I can express them as fractions. That's what a rational number is. It's a large group of numbers, okay? Now there's another set of numbers, and it is a separate group. There is no overlap at all between rationals and this group. They are separate. See, a whole number is an integer. A whole number is a rational. All integers are rationals. This group is called irrational. And irrational just simply means not rational. So, by definition, if I have a number that is not rational, it is not a terminating or repeating decimal, then it has to be an irrational number. Non-terminating means it goes on forever, or a non-repeating decimal that goes on forever. Okay? Irrational means not rational. In this scenario, since you can't write it as a decimal and you can't write it as a fraction, a lot of times we just have to leave it in simple form. You are familiar with some irrational numbers. Some famous ones that you will be familiar with are pi. So we can't write pi other than in this symbol format. We approximate it as like 3.14, but pi is the actual number. Another one that you may or may not know is e. You will learn about e this year. And you think, well, that's all there is, only two. Well, in actuality, there's actually many more of these types of numbers than there are these types of numbers. We just aren't familiar with these very often. So I'm going to show you a way that besides these two, how you can write as many of these irrationals as you want. And just think of this. Think of the square root symbol. If I take the square root of 4, I get the number 2. So 4 is a perfect square. So excluding all perfect squares, which are rational numbers, okay, the square roots of perfect squares, which are rational, every other one is an irrational. The square root of 2, the square root of 3, the square root of 5, the square root of 6, the square root of 7, the square root of 8. See? Any number that is not a perfect square, the square root of that number is going to be irrational. So you can see there's an infinite number. That's just the square roots. I can do cube roots, fourth roots, fifth roots. Anything that is not perfect, okay, is going to land in here. So you can see there's an infinite number of them now. These, all of these two groups combined form the real numbers. So the real numbers are the combining groups of rational numbers and irrational numbers. These constitute what's called the reals. So what is complex numbers then? How does that come into play? Well, I'm going to explain all that to you in just a moment. But in the nesting situation right here, let me explain. Now, I can't make it big enough to actually represent the size of the complex numbers in relation to reals. Okay? But every single real number is also a complex number. And then there's a bunch of numbers that are not real, that are complex numbers. And you'll see that it's quite large. So what is this complex number I keep talking about? What is this thing? Well, let's go back to this again. Okay, tell my little story again. So let's say back in the early days, the mathematicians saw this kind of thing, and they say, well, there's no real number that's going to work. So they say, you know what? Imagine that there is a solution. Okay? Imagine that there is one. What would it look like? What's its characteristics? Well, if I have a 1 here instead of a negative 1, if I have a positive 1, I would just take the square root of both sides. But we know that doesn't make any sense in the real numbers. But imagine that it does exist. This is what it looks like. The square root of negative 1. And because I'm a mathematician, I don't want to, write a bunch of stuff down every time. So since I say imagine that that does exist, let's just call it I, a lowercase I. So this I symbol is going to represent the square root of a negative 1, whatever that is. Okay? And that's the foundation of complex numbers. So a complex number is a number of the form A plus BI, where A and B are real numbers. This is what a complex number looks like. It's a two-piece number. It has a real part, and this right here is the imaginary part. That's what they call it. It exists. Complex numbers is the foundation of your entire computer graphics industry. The entire cartoon industry, Pixar, and all that kind of stuff. They have programs on their computer that draw that animation. Your video games that look almost real lifelike nowadays. It is all based out of complex numbers. Okay? And so they have equations that do that kind of stuff. And we'll talk more about it later. So how do I, like in a real number, here's the real number line, correct? Here's the real number line, here's 0. And we put these little marks in here to give me kind of location. And every little dust particle in here represents another number, whether real or rational or irrational. Everything here is a real number. So how do I graph a complex number? So if I put a dot here at 2, that means the number 2. So how do I express a complex number? How do I do that? It's a two-part number, correct? Well, it kind of doesn't have a number line. It has a number plane. So you have kind of like an XY axis, but it's not XY axis. This is the real axis. This is the imaginary axis. But it looks just like the XY axis. You got these little marks here for the real numbers because this is a real number line. So there's your 1, 2, 3, 4, negative 1, negative 2, negative 3, and so forth. And then the imaginary axis is the same thing, just like the y-axis. So there's your 1, 2, 3, 4. And there's your negative 1, negative 2, negative 3, negative 4. So this is your complex number plane. So to graph a number, a real part and an imaginary part. The real part means you go to the number line, the real number line, and then the imaginary part, you go up and down on the imaginary line, just like an XY coordinate. So if I graph the dot right here, that dot right there represents the complex number 2 for the real and 3 for the imaginary. So it'll be 2 plus 3i. That's that dot. That's how the numbers graph. So what if I put a dot right here on the real number line? Well, if I was graphing in the real numbers, it would just be a dot at 1, wouldn't it? That's a real number, isn't it? So what is this dot, though, called in the complex number system? It is 1 on the real and 0 on the imaginary. So you have to write it as 1 plus 0i. But please remember, every single real number is also a complex number. Here they are. Every single real number is a complex number. So every real number you can think of in the complex world is that number plus 0i. The entire real numbers are just this number line right here. All this other space, forever and ever and ever, all the other directions, that's all the other complex numbers that are out there. So you can see the complex number plane is much, much larger than the real number plane to our senses. So this point over here, if I put a dot right here, would represent the point -3 on the real, -1 on the imaginary. So I'd write -3 minus I. And that would be the name of that point. So that's the graphing stuff. This is how I would represent it on a graph, a complex number. Now, these actually do exist, even though they're not real. Mathematicians have gone through and showed that it is a numbering system based off of how they define numbering systems. And a lot of things then apply. For example, we now need to learn how to add and subtract complex numbers. If I give you two real numbers and I put a plus or minus sign between them, we know what to do. Well, what happens if I have complex? How do I add or subtract? Well, let's get an example. I'm going to show you an example with subtraction. Addition would be there's just a plus sign there. You're going to do the exact same thing no matter what. So here's an example. And what is 1 plus 3i minus 4 minus 5i? And I put in the complex numbers in parentheses so that they stand out. Okay? It is a common practice to do so. How do I do this? Just see the I as a variable. Okay? Even though it's not. It's not a variable, but you can treat it as if it was. So in other words, just distribute the negative and combine like terms. This would be 1 plus 3i minus 4 plus 5i. And then add the real parts and add the imaginary parts. So this answer becomes 1 minus 4, -3. 3 plus 5, 8i. Done. That's all there is to it. So adding and subtracting the same thing. If it's subtraction, just distribute that negative sign and basically combine like terms. How do I multiply? Okay, well, let's do the same thing. Here's the same ones. What if I want to multiply these? Times 4 minus 5i. I bet you can kind of see the technique that's going to pop up real quick here. You're just going to distribute this using the distributive property. So 1 times 4, 4. 1 times -5, -5i. That times that, plus 12i. That times that is a -15. I times I is I squared. Just like you would if it was any other letter. So now the question becomes is, what in the world is I squared? Well, to answer that question, I want to show you this thing that you might want to remember. Okay? The cycle of I to the 0 power. Well, remember, that's an exponent. Anything to the 0 power is 1. What is I to the 1st power? Well, that's just I. What is I to the 2nd power? Well, I, by definition, is the square root of a -1. So if I square both sides, then I squared must be the square root of -1 squared, which cancels the square root symbol, correct? And I'm left with what? -1. Because remember, where did this come from? What number squared equals -1? I squared equals -1. That's its definition. Well, what's I to the 3rd power? I to the 3rd power is just I I times I squared, isn't it? So I times I squared will be a negative 1 times I, or a negative I. What is I to the fourth power? I to the fourth power is just I squared times I squared. I squared times I squared is I to the fourth. But I squared is negative 1. So a negative 1 times a negative 1 is positive 1. And what happens is I have a cycle. It's a cycle of 4. So the I exponents will repeat these 4 values every fourth one. Okay? So I squared we now know is negative 1. So this problem becomes 4 minus 5I plus 12I minus 15 times a negative 1. So this term is going to change sign to become plus. So this is positive 15 plus 4, 19. I got a negative 5i's plus 12. And there you go. So that is multiplication. Please be aware of your I cycle for higher exponents of I. So what's next? Well, before we do division, which is what you probably were thinking, I need to talk about this thing called a complex conjugate. This conjugate term is going to come up quite often. This is what it looks like for a complex number, a complex conjugate. It's literally just this right here. So here is a complex number. Its conjugate is basically that. So you just change the sign in the middle. Okay? These are called conjugates of each other. Notice that they basically follow the format of the difference of two squares. Can you see it? If I multiply these two values together, anytime I multiply conjugates together, this thing is going to happen. This is the difference of two squares. So I already know, but I can multiply it out. If you want me to, I can just multiply it out. So I'll get a squared minus abi plus abi minus b squared I squared. Well, look at the two middle terms. They're going to drop out, aren't they? A squared minus b squared, but that's an I squared, so that's negative 1 also, correct? So that negative 1 turns that into a plus, and I get a squared plus b squared. Conjugates, when you multiply them together, will eliminate that I, which is really just a square root. So you can, they're actually as irrational conjugates too. Anyway, so there you go. Conjugates. We want to make sure we know what they're doing, what they are. Why do I need to know what a conjugate is? Because I need it to divide. Let's look at that example again. 1 plus 3i over, this is the one I did, so let's do this one, 4i. And they're in parentheses because they're complex numbers, and I'm indicating that they are the same, they are a number, okay? How do I divide this? Well, again, I want you to think for a minute. I, by definition, is the square root of a negative 1. And you cannot have a radical in the bottom of a fraction. So you have to what's called rationalizing. Well, in a situation like this where there is more than one term, I need the conjugate to do this. So to find this, you literally multiply the top and the bottom of this by the conjugate of the bottom, because I don't want this I in the bottom anymore. And the only way to get rid of the I is by this approach. See, I showed you. That's how it gets rid of it. And so you're going to multiply the top and the bottom by the conjugate of the bottom. And that's the conjugate of the bottom. So you can multiply the bottom out, but because you did the conjugate, you should know what it's going to be automatically. It is going to be 4 squared plus 5 squared. Right? If I multiply conjugates, it is the front number squared, and then the b part, not the I, just the b part, and the back square. And you're going to add them. The top one, you just got to multiply out. So we got 4 plus 5i plus 12i, and then we have plus 15i squared. Clean up the top, combining like terms. This will be a negative 15 and the 4. Negative 15 plus 4, negative 11. 5 plus 12, 17i. The bottom here is 16 plus 25. And 16 plus 25 is 41. Now, some people think you can stop right here. This is not proper. This is not in complex number form. Complex number form is an a plus a bi. This is a fraction form of something. Okay? This division is still in play. You actually need to split this apart. So you have to write it as a negative 11 over 41 plus 17 over 41i. If any one of these individual fraction pieces can reduce, you need to reduce it also. Little note to yourself, reduce fractions if possible. And that's how you divide complex numbers. So that's what you're going to be doing today in your homework and stuff. I'm going to stop the video right there.